Excellent. Hello, Buzz Portland, and Twitch as well, I guess, all the kids at home. My name's Kelly Gawne. Thank you for that glowing introduction, Will. And I am indeed a games engineer at Intel. So our technical title is DevRel engineer. It's the same thing that Antoine was working with Seth on DayZ. It's basically a made-up title that means we do performance optimization on AAA games. So obviously optimization is near and dear to my heart. It's pretty much everything that I do. It is my day job. But I could understand why you guys could be here, and you're game makers, not optimizers. At the end of the day, for you, it's about making a game that people love and want to play. So why would you care? For one, I think we've all had the experience where we've gotten ourselves like really hyped up for a game. It's about to release and we've been waiting for it for so long, or it's just a game that you kind of wanted to play, but you're not at your home rig, you're traveling, you're on a laptop or something, and you're like, you know what? Let's try it. Let's just fire it up. And then you end up here. The game takes 5 minutes to load. When it does finally load, you're watching a slideshow. And you're like, no, it's okay. Like, I can make it through this. And then you just end up so nauseous if you're trying to play an FPS, or just so frustrated because the frame rate's so low, the physics aren't working right. It's miserable. So basically what happens then, your gamer who is playing maybe your game in this case, gets frustrated, they turn off the game, and you've turned someone who was a champion of your game into an enemy. They're either never gonna play it again, or they're going to assume that you just disenfranchised all these people who don't have a rig big enough to play your game, or at the worst case, they're gonna go out and become your enemy, the person who's online bashing you. So with that in mind, I say, let them play. At the end of the day, optimization is something that not a lot of people think about, and it's very easy to push off because you think it takes either too much time, or because people feel like they don't have the know-how to do it, or they just don't have the desire to do it and don't know why they should have the desire to do it. And so what I'm hoping today is I can give you the know-how, I can help you figure out how much time to dedicate to this, and hopefully by the end you'll have the desire to do it in the first place. So, agenda. First, we're going to start with a little bit of optimization thoughts. A lot of this is going to harken back to things that Seth was talking about. Then we're going to go through some profiling tools that I use with Unity and Unreal on those games in AAA settings and indie settings. It applies across the board. Just a quick survey. Let's go ahead. Raise hands if you are a Unity developer. Yeah, nice. All right, raise hands if you're an Unreal developer. That is about what I expected. So for the folks at home, that's about everyone is a Unity developer, and we have our holdouts, about 10 people that do play with Unreal. So this presentation is going to be skewed a little Unity. That's about what I expected. If you are interested in deeper Unreal optimizations and more into those systems, I'm going to kind of gloss over some of them, but I'm happy to talk to you later about more in-depth problems and specific Unreal things. Then we're going to go over some quick tricks and pitfalls that we see regularly with like Unity and Unreal that can hopefully help you out. And questions, always questions. So, optimization ideology. When should you optimize? Don't. It really is, as silly as it sounds, I'm a big fan of the whole idea if it ain't broke, don't fix it. It's a matter of testing to make sure you don't need to fix it. So, but if you test and you're hitting the frame rates you want, the resolutions you want, on all the systems you want, I may go ahead and say, try something a little bit below your min spec and see if you're close to hitting it. And if you are, then maybe invest a little time. But at the end of the day, you have a lot to do. And if something's there and you have all the headroom that you want and all the features that you want, then don't optimize anymore. Next, don't yet. So if you start off trying to optimize everything when you add it, if with every model you add, you're like, oh no, I have to make sure I add 50 LODs for this, and I need to make sure that this physics system is as absolutely, I'm using all of my object pooling on every single bullet and all of that stuff, you're just gonna shoot yourself in the foot. You're gonna get frustrated, it's gonna take you 50 times as long. I think we all kind of know the best thing to do is to start hacking things together and then fix things as you need them, because you never know, you may spend all your time making those 50 LODs and it turns out your polygons are not a problem. You can fit that many triangles. That was never your issue to begin with, and instead you're doing a tick on every single one of your rocks, which don't ask me why you have ticking rocks, but Apparently you have ticking rocks, and that's making you have a CPU bottleneck, so it doesn't even matter if you're hitting the GPU problems. So wait until you actually know there's a problem and then start optimizing. Wait until you actually are getting towards content complete. A lot of times when we work with AAA games, we won't start working on optimization until they're at least 75% content complete, or until they're about like 6 months out from launch. So they have most of their systems in place and are moving into an optimization phase. When you do get into optimization, again, it's a matter of don't fix problems that don't exist. Profile first. Profile, let the data tell you what the problem is, and then address the biggest problem you see. It's easy to go and look at that and see, oh, well, I have, these 7 things, I gotta go fix each one. But the problem is a lot of time with bottlenecks, like Seth described, it's a pipe, it's a flowing water pipe. And sometimes if you fix one thing, then you'll see the change cascade. So things might have been one problem that was actually affecting all 3. If you go and try and fix all 3 at once, you might just get yourself confused or frustrated. So always go kind of one by one. When you are ready to start addressing the problem, you want to make sure that you test, gather data. So if I say, okay, well, I do have this model that's 1 billion, polygons. Please, dear God, do not make any model with 1 billion polygons. But if you do, then you test it. You say, okay, this draw is taking me 45 milliseconds. Write down 45 milliseconds. Then do your LODs, address the problem, and then test it again. You're like, oh, go me. Now it's only 2 milliseconds, which is still kind of long, but better. That way, not only have you proven to yourself you've solved the right problem, but you can throw it on your status report and tell your boss or your mom, whoever cares the most. And then the whole thing is just a process. You do it over and over again. So you go back all the way to the top. Am I optimized? Am I where I need to be? Do I need more headroom for another feature I want to add? Or am I okay? Can I just chillax? Add more features and then come back and optimize again later. And then just go through the whole list again. It makes it a lot easier because a lot of times people just like, I'm in the optimization phase, I must optimize everything. But really just do as much as you need. So the core question that we're always asking, what is your bottleneck? Nothing else matters. If you have a problem, it is a pipe, you want to fix the blockage in the pipe and let everything else flow. And the only way to figure out what your bottleneck is with profiling. Yes, this is a shameless GPA plug. Really, this is actually a Unity sample made by none other than Cristiana Ferreira, who will be in the VR panel later, that talking about some of the optimizations and things. It's our system analyzer up there. But really, when you work with Unity Unreal, and you guys, since you are the developers of your games, you have the benefit of having source access, you have a lot more tools at hand. So, a profiling toolbox. Is that readable for you guys? Mostly. So for Unity, there's some really quick, easy things you can do. As Seth said, the most accurate data is always going to be the best at the end of the day, but sometimes when you just need a quick look, there's some great tips you can use. Unity has a little render stats overlay that's just literally a button you click that gives you a lot of info. The Unity profiler, of course. Unreal, the stat system is beautiful. There's Unreal Profile GPU if you want to get into a more frame-by-frame basis. And Intel GPA is... to be honest, I'm an engineer at the end of the day. Like, I use the thing that fits my workflow. I wouldn't talk about Intel GPA unless I actually found it super helpful for what I do. And I think it's pretty essential, especially when it comes down to profiling exactly what's happening within a frame. I think it's one of the places that the engines struggle a little bit right now, and it really fills a gap in the workflow. So your core questions is, it's CPU or GPU? Again, as Seth talked about, some things that you might see as CPU limitations. He was talking about draw call preparation. So before you send things to the screen, you're basically taking all of that models you want to draw, all of their associated textures, wrapping them up. You send that to your driver. The driver sends it to the hardware, executes, and then you have a beautiful image on the screen. Depending on the way you batch those or organize them or send them off or stick them together, you can end up having CPU limitations if you have lots and lots of draw calls. Scripting, as we said, like if you're ticking on 1,000 rocks, I will find you. And then physics, of course, PhysX does execute on the GPU in some cases, but it's important to know kind of what engines are using PhysX to do those things on the GPU. Unity largely does their physics on the CPU. So if you're having problems with physics, that'll show up in the profiler. Kind of the hidden thing that not many people talk about in terms of bottleneck is memory could almost be its own section, like CPU or GPU or memory bandwidth, because it affects both your CPU and GPU. So that's a matter of, are you dealing with huge textures? Do you have in a deferred renderer like this giant geometry buffer? That's really something that can hit you on both sides, and you'll end up, in some profilers, it'll just look like both your CPU and GPU are underutilized, and you won't figure it out until you go and look at all your textures and you're like, oh God, what have I done? As far as the GPU goes, a lot of these things we already know. Of course, memory bandwidth. Resolution's a big one, choosing a resolution to make sure your game doesn't end up pixel art when it doesn't have to, but also as actually functional. Shader complexity, geometric complexity, generally more shader than geometry. And of course, lighting is probably almost always the number one. So yeah, that's kind of an idea of the things that might hit the CPU versus the GPU. So here's how we'd find those things using those tools. So if you're using Unity render stats, you get a lot of different info right off the bat. You're getting your FPS, which, minor diatribe. If you use FPS as a marker of your improvement, your performance improvement, you just need to remember that FPS is inverted scales, so the difference between, it's kind of like miles per gallon, the difference between 15 FPS and 30 FPS is not the same as the difference between 30 and 45. You actually generally, that's why a lot of times people use milliseconds per frame instead, because it's a different scale and it's much more reliable. So a lot of times when we report performance improvement, we're doing it based on milliseconds per frame. Other than that, you'll get your FPS, you'll get your batches, basically how many draw calls you're wrapping up together, poly count, resolution you're playing at, things like that. It's just kind of like a nice quick view while you're in game if you just want to be like, oh, okay, how am I doing right now? That'll give you a nice preview. And as you can see, we'll talk about batching later, but it does give you your batch count right there, which is nice, especially for cracking down on some of the driver overhead in between draw calls. So the Unity profiler is super useful for scripting issues. I find it to be less useful for GPU issues, possibly because I'm more used to GPA, but go ahead and give me a shout out. Is this CPU or GPU limited? Anyone? Go for it. GPU, excellent. So your GPU is at 100% utilization this entire time. Your CPU is, stumbling along, but basically anytime you see your GPU at 100% utilization, you are probably GPU bottlenecked. So you can see that, seeing that in the profiler is one way to see it. There's a few other tricks to see it different ways, but the profiler is really great for figuring out. This would absolutely tell you if you have like problems doing too many ticks or things like that, or if you had a weird script that was, taking a lot of time. It'll also help with like some of those memory issues too. It'll show garbage collection and things like that. As for Unreal, a quick gloss over. Some of the really useful stats just right off the bat: unit, slow. Those are going to be kind of the same thing as the Unity stats overlay. It's going to be your brief CPU thread time, GPU thread time. Scene render is going to show you a little bit more of the driver overhead things you're interested in. Like here you can see, it's in the bottom, the third one down. It's probably illegible, but you can see your mesh draw calls, which is again like what your CPU is saying in terms of draw calls. Your game thread, GPU, exactly what each pass is taking, so that's very helpful. Unreal also has a little bit more helpful, a profile GPU function where you can take a frame and actually look at it and break it down by pass, which is kind of what we get with Frame Analyzer, but not quite. System Analyzer, of course, as Seth said, is like Task Manager on steroids. This is really useful if you feel like you need more hardware metrics. It's really helpful especially when you need to do those experiments. The quickest way to figure out if you are GPU bottlenecked is to do that experiment to see if you're on like null hardware, or if you need to disable draw calls and your frame rate skyrockets, then you're GPU bound. There's other ways to check that. You could decrease the resolution, and if your frame rate increases, you are probably GPU bound. And there's a lot of ways to check that, so it's kind of pick your poison. The one thing that I do think is kind of indispensable from GPA is the frame analyzer. You can see what the biggest problems are. There's a bunch of different views that'll actually highlight the geometry that is a problem, which is something that I know that engines want to do but haven't done right now. So that's where I find, like, if you have a part of your game you find very expensive and you can't figure out why, you know it's something on the GPU, I'd really suggest taking the time to spend, 15 minutes to an hour, just try out GPA, figure out, and it'll show you right away, like if you have that really bad geometry right up front, or if you have a shader that's gone out of control, things like that. So where's the bottleneck? Unity, Unreal. Basically what you're going to do is you're going to play your game. You're going to roll around and watch your frame rate. You can either do this by actually taking a graph. Unity has the profiler, which kind of records backwards a little bit. You can actually dump a file with Unreal, which is really nice, and just look to see where in your game frame rate starts tanking, and that could be like either a shader that's gotten expensive, or an area that's triggered, or if you've moved from one load level to another load level, it's loading in a bunch of textures, things like that. As we said, if you decrease the resolution and the frame rate improves, you're very likely GPU bound. GPA is nice. You can actually run the experiments. This is a little bit uncommon. You don't generally end up being bound on the driver, but there is an experiment that will let you help you see whether or not you're bound on the GPU or on the driver. I can tell you 99% of the times you're going to be bound on the GPU and the driver won't be in the way, but just in case, you can try null hardware, and then if it still didn't increase, try disable draw calls, and then you're driver bound. If neither of those experiments help, you are CPU bound, and so go down that path. So we're next. If you found out you're CPU bound, then you're going to go to the Unity or Unreal profilers, like because you have the benefit of source access, like that can give you a lot more information. You can see things like, is this a constant cost? Is this across the board? Okay, I'm noticing that this tick here is always taking 8 milliseconds, and what is that doing? Or is it something where as you move around the level, you'll see it periodically spiking? That can be things like garbage collection, or it can be things like moving into a new area and loading something. As for your GPU side, you want to check, like, is there one killer draw call that's bigger than everything? A lot of times there's kind of a trick too, because it will be your lighting, and there's not a ton you can do to downplay your lighting other than, reducing your number of lights or checking out the shader and see if there's anything you can do, but a lot of those are engine-built shaders. Or there are a lot of little calls like we saw in DayZ, because those over time can accumulate and it just stalls out your hardware. And is everything rendered essential? I can't tell you how many times I've seen people rendering geometry that is never visible, or they render fog that you can't actually see, or like an entire different part of the map at the same time, or they're playing the intro video while the game is still playing. There's a lot of strange things out there. Optimization is a scary world. So again, profile, optimize, profile. Like, check to see what the actual problem is, then go address that problem, and then come back, check to see what the actual cost change was. So if that tick took 8 milliseconds, go see what you can do to reduce that. Okay, I don't need to tick every frame. Let's just tick every, 0.02 millisecond or 0.02 seconds. Come back and you're like, oh, okay, yes, that has reduced my frame time. I'm now at 2 milliseconds for this pass. So this next section is going to be a bit more potpourri. There's no one solution for every game. Every game is different. I can tell you things that we see a lot on Unity, we see a lot on Unreal, but at the end of the day, there's no game that I haven't seen something weird that I've never seen before on. Like, there's always something strange which is kind of cool, like you're always learning, but it does mean that there's always more to learn. So this is going to be kind of an overview of things that we generally see that you might see in your game. And so if you see things in the profiler that indicate this might be the case, these are some quick tricks for you. So, scripting problems. If you're noticing in the Unity profiler and stats that your ticks are taking a long time, or some specific tick or some physics update or something like that, these are some things that might help. As I was mentioning, if you are updating your rocks every single frame, again, I don't know why you're updating rocks, but stop. Check to see if you need to do that every frame. A lot of times you don't need to use game tick. You don't need to use fixed update. You can actually, in Unity, you can create coroutines. There's a way you can do the same in Unreal by like setting your blueprints to run at a fixed time step instead of every single frame. A lot of the time, you don't need things running on every frame. Or you may need them running more than every frame, like your physics. So just keep an eye on if you have a really expensive ticks, do I need this updated every single frame, or is it something that I can do more long-term and let it fill out a little bit more? Scripting fades. This is kind of a weird one that I'm hoping more people learn about. If you ever do like a vignetting effect, you know, where in some shooter game where it turns your screen red and then you can't see anything, and it's really annoying. A lot of times the way people do those fades, so as you get healthier magically, the vignette kind of just disappears. The problem is in Unity, depending on the way you script that, you could still be drawing that. And the thing is, anytime you do a draw call, it's going to be as expensive as many pixels you touch, right? So if you're touching, with a vignette effect, you're touching every pixel on the screen. It's called a full screen pass. And especially on lower end hardware, a full screen pass will always take about a millisecond with current hardware. So you've just cost yourself a millisecond for something you can't even see. So you have to make sure that when you're writing that way you script that, you make sure to disable that object, not just turn down the alpha and let it sit there, but actually disable the object once the alpha reaches 0. As you can see here, this is, again, one of Christiana's wonderful samples. This is the GPA view at the bottom, so those highlighted yellow blocks there are the draw calls that are happening, and they should disappear over here, and they don't. That means you're still drawing them. Don't do that. Scripting with memory in mind, it's important to remember when you use Unity and Unreal, they are doing garbage collection. In order to reduce that, there's some tricks you can do, especially like, you'll notice it because you'll have these kind of spikes. So if you're using a lot of memory, then you'll see these spikes showing up. There's a few different ways to reduce that. Reuse objects as much as you can. Keep them in a pool. This is common knowledge for if you're doing like bullets or something like that. Instead of creating a new bullet every time you need to fire from the gun, you create 30 bullets and you have them like in a little cache, and then you just use them, and then when they're disabled, you put them back in the cache. Explosions is another one. The catch-22 is that if you really only needed 2 bullets, you've created 30. And if you do end up using like a lot of them and you create, a cache of like 150, then you could end up going the other way, and now you're increasing your garbage collection as well. So it's kind of a game. Again, profile. See if this is your problem. Change the number, profile again, see if it fixed the problem, and that's pretty much the way to address that. As far as garbage collection avoidance, again, I would not do this unless you are having a problem with it, but you can get into the nitty-gritty of using structs instead of classes, caching references to objects and things like that, and then minimizing your runtime allocations, which is that, creating a bullet when you need it instead of using the pool. Try not to do that as much as possible. Physics. So there's one thing that I'm sure anyone who's used Unity before has probably had beat into them with any kind of physics that I've done, which is don't move static colliders. They're called static. You've checked the little box that says, I'm not going to move this. Please do whatever optimizations you want. And when you do move those, you're going to see exactly that. It says, it'll say badcube.fixedUpdate, and underneath it'll say staticcollider.move. This will show up in the profiler. It'll be really easy to see. I think they even added a nice little warning anytime you have a static collider move to just be like, hey, stop. Other things you can do, primitive colliders are always going to be cheaper than mesh colliders. So, you know, those, you only get a few shapes. You get like a box and a capsule and I think a sphere. But anytime you can use those instead of actually a mesh collider, then you're going to save yourself a lot of expense. You can also tweak your fixed delta time like we were talking about earlier, kind of the similar idea to coroutines. If you don't need hyper accurate physics, then there's no reason to be updating it at 144 hertz. You'll find this a lot with, if you're trying to do like really detailed rope physics, then you may have to turn that up, but just know that you're turning up the physics tick across the board, not just for that object. Don't move static colliders, and if you need to move something, add a rigid body and uncheck static. A lot of times optimizations in Unities just comes down to, did you check this box? Should you have checked this box? Uncheck this box. So check your boxes. Model geometry, so this is a little bit more for the artists of the room. A big thing that sometimes people forget about, the number of vertices your GPU is actually going to process is much larger than the number of vertices that you have created in that model. So I could create, you know, a 10K poly model and be like, oh yeah, this will be totally fine, but my UVs are all over the place, I've got tons of hard edges, and so it turns into, even though I think it's a 10K poly model, my GPU has to process it like it's 100K. And that's not unheard of. So one of the things you have to think about is making sure that, one, you do minimize the triangles you need. If there's no visual difference, there's a lot of great lotting tools out there right now. Unreal has some built in that'll help you scale nicely. Take a look at it at the lower poly amount, and then see if that's still a visual quality you feel comfortable with, and then make sure you're reducing UV seams and hard edges. As painful as that can be. I'm sorry, all the UV editors out there. Also, when you can, and when it's the issue, when it is your bottleneck, use level of detail. Again, tell your artists about this early so they have time to do it. This isn't something you're gonna get done the day before launch day, but Unity and Unreal both have really nice systems that are very friendly in terms of like helping you determine where you need to put your switches in and make sure you test to make sure those switches aren't too jarring. But it makes things a lot easier. For example, on the left, that's like a 7K and a 5K poly building. And then on the right, we've reduced them 10x. So it's a 400 poly building and a 300 poly building. And how much can you tell? So. And sometimes you can really tell. It's just a matter then of changing your LOD distances. All right. The other thing that you get kind of for free in Unreal, but you do have to do a little bit more work in Unity, is that you have occlusion culling. So occlusion culling is basically the idea of right now, so if I were a game engine right now, and I were to render my view of all you beautiful people, I would draw everything in this room, and if I were not using occlusion culling, I would draw that building and that tree and the buildings over there and all the cars on the sidewalk. Basically, it's the idea that I know about all the geometry that is in front of me, whether or not I can see it the way a human can see it. Occlusion culling helps fight that and helps reduce how much drawing you have to do, because it will say, okay, I'm going to use that wall as an occluder, and everything behind that wall I can't see, so I'm not going to draw it, I'm not going to process it. Again, with Unity, I'd recommend just looking up their page on occlusion culling is pretty helpful, and it'll walk you through everything really nicely. This is especially useful for kind of hallway first-person shooters, think like Doom or System Shock. Those are things where you really should be using occlusion culling. Less helpful for giant open outdoor worlds because you don't have big enough occluders. So that's when you need to be a lot more aggressive about level of detail instead. So batching and instancing. I think I'm actually going to switch this order. You saw nothing. Batching and instancing are not the same thing, which is something that can be very confusing in forums because people will call them the same thing a lot of the time, but they do actually execute in a different way. Both of them are meant to help reduce cost in terms of like the driver, and in instancing's case also in terms of just how many draw calls you have to execute. Batching is the process of taking a bunch of objects that all use the same material and saying, hey, instead of doing this material, this material, this material, back and forth, I'm going to say, oh, I'll do every object with this material, then I'll do every object with this material, which is why you see people pushing texture atlases, because the idea is that if you have a mega texture that you can share between all these objects, the driver doesn't have to switch. Like the engine doesn't have to say, okay, set this resource and then set that one, and then it's evicting things from memory. So it saves you a lot that way. Batching kind of comes for free as well on static objects in Unity, but there's a couple of tweaks that I'll talk about. So the whole idea, if you had 30 materials using 30 meshes using materials A, B, and C, instead of going A, B, C, A, B, C, A, B, C, it'll do 10 with A, 10 with B, 10 with C. But the important thing to note is you're still doing 30 draw calls, which is not necessarily what you want to do. So that's when instancing comes in handy. Instancing can actually reduce your number of draw calls. So if you do like have, like the disabled draw calls we were talking about earlier, or if you are noticing like a lot of CPU cost trying to set up those draws, that's when you want to look at that. The instancing largely means you're using the same mesh and the same texture. So it's the exact same object. They use this a lot with rocks, and then you just rotate them to make them look special. And instead of having 30 draw calls, you'll just have one draw call. This gets kind of tricky sometimes when you're doing culling because they're considered kind of one mesh. Even if I'm looking at one rock, I'll still draw all the other 30 rocks. So all those other 30 rocks are still going to get processed. But a lot of times with instancing, they're lower poly meshes, so it ends up not being a huge cost anyway. So batching. Unity automatically performs batching on objects you've clicked the static on. So really all it is, it's also batching will not affect culling, so it will properly cull all those things and not draw them. But the thing is, it's not going to matter unless you are sharing textures and using like that kind of texture atlas to help reduce the memory cost. So what you are going to get back from this is if you're having problems with memory overhead, this will help. This will help between switches of memory, so you won't thrash as much, but it is at the cost of like you're now creating a texture atlas, which is a larger texture, which may take longer to manipulate. So just keep that in mind. And again, profile, optimize profile. Always check to see if the thing you did helped. Dynamic batching, this is more for, if you're doing small particle systems, then you can process them all on the CPU. Less common, but if you're noticing that you have like a small system of particles that aren't behaving, you can try some dynamic batching as long as they're identical. Textures and shaders. Textures is pretty easy. Again, to help with batching, combine them if you can. Pretty much always use compression. Compression's pretty efficient these days. You probably won't even notice unless you are a robot. And as far as generating bitmaps, unless you have a 2D game or it's a UI thing, in which case, you're never going to see the bitmap, it's always going to be the same size, then you definitely want to generate bitmaps. It's worth the memory cost. It's like 33% memory per texture, so it's not even that bad. If you have memory bandwidth problems, then this is something to kind of think about, but at the end of the day, the amount of GPU performance you're going to get back from using these lower rates textures is going to outweigh the extra memory cost. So almost 100% of the time, use bitmaps, use compressed. Texture atlasing. In Unity, this is super simple. You can just say texture 2D.pack textures and then give it all the textures you want to be in one, which makes it nice because you don't have to make the mega texture yourself. And again, this is helping reduce your material and texture count, which is going to help reduce that thrash. It also helps with shaders, so they can sample from one texture instead of doing 50 different ones. You're going to reduce your engine overhead on material setup, on texture switch, and you're going to enable more static batching. As far as shaders go, you could do easily a full talk on shaders. Can I get hands for people who are writing their own shaders for their games? Okay, yeah, you're kind of a specialized crew, and there's tons of resources there to help. The main thing to keep in mind when you get something off of the Unity store or the marketplace, if you use a built-in shader, that shader is not built for your game. It just means that it's built to work with the engine and to be functional. It doesn't mean it's going to be optimized for you. If you are writing your own shaders, it's typical shader knowledge, reduce complex math operations. A big thing, don't try and write your own math operations unless you really, really need to. All of the drivers kind of know exactly how Microsoft implements those things, or how they're implemented in the HLSL, or so they look for exactly that name, and then they can use a fast path. So if you've created your own inverse square root because you're like, oh, I think I can do it faster, you can fight with the driver guys about that, because you're probably just going to end up getting a performance regression. As far as float versus half versus fixed, largely on desktop GPUs, they're all going to be treated as float, so I won't worry too much about it. Again, it's a matter of check your engine, check your use case, profile, optimize profile. Lighting and shadows. Again, this could be its own talk. The absolute cliff notes. If you're using a forward renderer, there's a forward path and a deferred path in Unity. If you're going to use the forward renderer, it basically just means the more lights you have, the more expensive things are going to get, because it's calculating those lights. Like, each object is calculated per light. So if I have 5 lights that are affecting the object, I will draw that object 5 times, is essentially the cost. So you have to pay attention to whether your lights are being designated as important, which means they're going to be per pixel lights versus per vertex or just general. And so keep an eye on that. The nice thing with forward is you get real-time shadows. The problem is that, yeah, exactly that. The more lights you have, the more cost you're going to add. Deferred, really, really quick. The nice thing about deferred is that you can add much more lights. You're just going to do all your lights in one pass at the cost of memory overhead. So you're basically going to process all your geometry on the front end and be like, okay, what is my albedo for this? Where are my normals? What does all of this look like? So you're trading like the heavier per geometry light compilation for this giant G buffer that can get very much out of hand if you're not watching it. So other things, semi-transparency, like you have to do a post-processing pass when you're using deferred if you want things like that, and your anti-aliasing. These are generally pretty included. The no anti-aliasing generally just means you have to add it on top. It's not that you can't add it. In fact, a lot of games that use deferred have some really great anti-aliasing on them. It's just you need to go and make sure that you've got all those checkboxes checked. The other thing that's a nice quick win if you are doing lighting is light mapping. It's beautiful, it's wonderful, please use it. You can basically put all your lights there, bake all of them, as long as you don't need them to move or flicker or anything, and you can get some really beautiful looking geometry at relatively low cost. I didn't include it unfortunately, but there's a great Unity demo where it's got like a scene of a barrel in a room, and they show it before light mapping and after light mapping, and it's just beautiful. So if you get the chance, it's a lot of free visual quality. And it's a pretty simple process in Unity. Just mark all your static objects and go through. Shadows, again, this could absolutely be its own talk. Real-time shadows are going to be expensive. Use them on as few objects as possible. If you can bake your shadow maps, please do. If you're using shadow maps, create different levels of detail. That's really helpful as well. These are some very Unity-specific things, but in general, they can give you a good, quick rundown. So, at the end of the day, though, these are all, this is just potpourri. I can word vomit at you all day on things that I may or may not have seen or suspect are problems or could be problems when you try different things in Unity and Unreal and make systems combat each other. But at the end of the day, it's all about, these are guidelines, not rules. You can use, some of these are going to apply to you, some of these aren't going to apply to you. At the end of the day, it's a matter of, do I see this as a problem in my game? If this is a problem in my game, what are solutions that I know could possibly fix this? Let me try that solution. Okay, that improved it. I'm done. So, with that, some final thoughts for you. Design with optimization in mind. This doesn't necessarily mean that you have to start optimizing right away. Remember, a lazy engineer is an efficient engineer. This just means that when you're setting up your milestones, set aside a little bit of time to be like, hey, this is when I'm going to kind of do a performance review and see how we're behaving on everything, and dedicate a little bit of time to dig into those things or learn a tool if you feel like you want one. Next, know what you want. So are you optimizing because you want more people to be able to play your game? You want to be able to hit more hardware? Are you optimizing because you want more headroom to add that like extra cool lighting feature that you can't fit right now? I've seen everything in between. It kind of depends on what you're going for. A lot of times, if you're doing an online game, then you want to get as many people playing as possible. Like Overwatch is a great example. That thing will play on a potato. Which is wonderful because now you have this really rich user base, people who can play everywhere on whatever system, versus like there are other games where, you know, it's single player. They don't care. At the end of the day, they just want you to be able to play and have a really rich experience. So if that's what you want, then just know exactly, you know, kind of what headroom you have, what headroom you need to fit in that feature you want, and just keep testing. If you see something wrong, before you try and fix anything, please, please, please go and get data. Numbers are your friend. They will point you in the right direction. Just make sure you're testing on consistent settings. So if you checked a checkbox and then something changed horribly and you forgot you checked the checkbox, which I have done this and I got really confused where we had a 2x performance regression on a game and I remembered I'd checked a checkbox that I shouldn't have. And my studio was very concerned, but it was all good. Just uncheck the checkbox and everyone was happy again. So yeah, when you see issues, profile first. Make sure you're profiling at the same settings. Again, profile, optimize, profile, go back, always start from the beginning. But at the end of the day, all of this is just about doing what we love, which is making fast, fantastic games. It's about making a game that as many people can play as possible and enjoy your work and enjoy the visual quality of the thing that you've invested so much time in. So I hope I've given you enough know-how to kind of get started, get your feet wet. I hope I've presented a method that'll help you do it in as little time as possible and, you know, reduce that overhead. And at the end of the day, I hope you guys now have the desire to go make fast, fantastic games. Thank you. I think we do have a little bit of time for questions. If you guys have anything, if it's super specific to your game, I'm happy to talk to you afterwards, but anything. Yeah, go for it. Okay, so the question was, what's the first big step you make in a Unity project to make it not look like a Unity project? That's a great question. The big thing that a lot of people forget about is taking advantage of like those light mapping systems, of using reflection probes, of adding those things in, because they think, oh my gosh, oh no, if I use that lighting quality, it'll be really expensive. But it's something that if you leverage those tools, like if you use your shadow mapping, like all of that stuff, it can look really nice really quickly. There is kind of a matter of like Unreal does give you a little bit more visual quality for free, but it's not that you can't get those things in Unity. It's just a matter of you need to go and look at how the shadow system works. What are the right settings to be using for your game? How do they fit into your performance profile? And then, yeah, it's a matter of tweaking that until it looks the way you want it. Good question. Go for it. What does it mean for your textures to be compressed? So basically there's and how does it help you? So texture compression, a lot of the algorithms they use for texture compression these days, so they'll take whatever texture you're inputting and they'll basically, in some ways they can do this losslessly, so they'll basically just move it into a smaller size. And because it's a smaller size, it's easier to transfer between the CPU and GPU, it's easier to manipulate, and it basically can give you some free headroom in terms of using that texture in whatever places you want to. Okay. Yeah, no problem. Anything else? Throw me a softball. There we go. What are mip maps? Great question. I'm sorry, I should have gone over that. So a mip map is basically when you generate mip maps, what it's doing is it's taking your nice big 4K texture. Please don't use 4K textures on low-end systems. Takes your nice big 4K texture and it's going to generate a 2K texture and a 500 by 500 texture and smaller and smaller. And what it's going to do is it's, as that object gets further away, it's going to naturally switch between the textures for you. So that way, if an object's really far away, you don't need a 4K texture on that. It's filling 4 pixels on your screen. So in that case, it's going to use like whatever the smallest bitmap it has. So it helps a lot with the sampling. Okay, so why do I suggest not using bitmaps for 2D games? A lot of times the reason is because exactly that, like the bitmaps are going to switch out as that object gets smaller and farther away. So if it is a matter in your 2D game, your object is going to get much, much smaller or like inflates in size or decreases in size rapidly. That may be a good case for it. In general, like the Unity recommendation is not to, only because that's not a super common thing that you see in 2D games. But you're right, exactly that. If you are inflating the size and decreasing the size in your 2D game, you may want to go ahead and generate bitmaps for that object too. Go for it. So are there particularly common problems you see for optimization in 2D games? Honestly, it's a range. I've seen, there's a game in particular that just really gets my goat because I just want to optimize it. Sometimes people use particle systems in 2D games where they're just using a ton of particles, more than you need in order to get the visual quality that they want, and it's just tanking performance. So I'd keep an eye on like your effects, especially background effects you're doing, because particles look cool, but at the end of the day, those can get really expensive really fast. They're super easy to see in a profiler. The way you can address them, you can either reduce the cost of drawing each of those particles, make sure they're batched. That's a case for dynamic batching, or things like that. Other things you might see, expensive shaders. I've seen some very strange, expensive shaders before, so that's a matter of kind of going in, do I really need this shader? Is it doing too much work? Am I using really expensive functions like powers and square roots and giant looping functions? And those are kind of things you'd want to watch out for. Yeah, no problem. Anyone else? Yeah, go for it.
So when you're dealing with like image buffers and lots of layers of things being drawn to the screen, how do you deal with optimizing or basically drawing what's only going to be on the screen versus stuff that is like behind things and basically parts of images that are like behind things and.
Okay, so if it's like, if you have like an image overlaid over another image that's like partially covering it. So I haven't worked a ton with like 2D image layering. There's a few things you could do in terms of, I wonder, I would have to see exactly how Unity's handling like occlusion on 2D systems, but to some degree there's a way you can break down, at least with 3D systems, you can break down a mesh and then it can treat those different parts separately. So it could occlude one corner and then keep going with the other 3 corners. And that way it would save you rendering that entire corner there. So that's a trick we use on like super large meshes, like a mountain. We would split into like 4 different meshes so that we can cull it instead of drawing the whole mountain when you can't see it. So that might be one way to do it. I'm not specifically sure about that problem, but I could check it out and see what I can find.
Yeah, that's like, because otherwise you have to like process every pixel for like each image and stuff like that, and that would be expensive.
Yeah.
So like how do you, so I guess like.
Yeah, part of it too.
Shader or.
Yeah, well, it's not necessarily a certain shader, but you could play some tricks too with like as the image gets overlaid, like reducing the quality, like using if it's playing a movie or something, you could use a lower resolution movie, or that could be a case for like some kind of map if you wanted to. But yeah, it's a matter of exactly what fits your case. So, thank you. All right, anybody else? Wonderful. All right, with that then I will bid you adieu. And then I think next up we have lunch. So thank you for listening with your empty stomachs.